Vyakhyaan of the series of 75 episodes, series of Vyakhyans, which is being organized as a part of PRL's 75 years of legacy and history in fundamental physics and space sciences. Established in the year 1947 by the father of Indian space program, Dr. Vikram Sarabhai, the PRL's Platinum Jubilee coincides with India's 75 years of independence. Hence, it's a joint celebration of the development of science and technology in India by PRL under the banner of PRL Ka Amrit Vyakhyaan. Today, we have yet another very distinguished Vyakhyaan the speaker, Professor Phil Christensen, who is a professor at Schools of Earth and Space Exploration and Geological Sciences at Arizona State University. We thank Phil for accepting our invitation and joining us in Platinum Jubilee celebration of PRL. I would request my colleague, Dr. Durga Prasad, to kindly introduce Phil to our audience on WebEx, as well as those who have joined us live on YouTube. Over to you, Durga.
Thank you very much, sir. As mentioned, today we have with us a very world-renowned planetary geologist, Professor Phil Russell Christensen. Welcome, sir, for our 42nd PRL Ka Amrit Vyakhyaan of our 75 Vyakhyans or colloquium series. So to introduce, Professor Phil Christensen is currently a Regents Professor and Ed and Helen Corrick Professor in the School of Earth and Space Exploration, SESE, at Arizona State University. He received his PhD in geophysics and space physics from the University of California, Los Angeles in the year 1981. His research interests focused on the composition, processes, and physical properties of Mars, Earth, asteroids, Europa, and other planetary surfaces. Professor Christensen mainly uses spectroscopy, radiometry, field observations, and also numerical modeling to study the geology and decipher the history of planetary bodies and their moons. A major part or facet of his research is the development of spacecraft instruments. As a principal investigator or co-investigator, he has built and led several science instruments that have been flown on NASA's Mars Observer, Mars Global Surveyor, Mars Odyssey, Mars Exploration Rover, OSIRIS-REx, and Lucy missions, and the UAE's Hope Mars Orbiter. So one of the outstanding thing is the Themis, which has a longevity record on Mars Odyssey. He is currently developing an infrared camera for the Europa Clipper mission. Over the past 20 years, he has developed an extensive K-12 education and outreach program to bring the excitement of science and exploration into the classroom, and he has mentored nearly 32 outstanding PhD students. He has several awards and honors to his credit. The list is, of course, very long, but I should mention a few here. So Professor Christensen is a fellow of the American Geophysical Union and the Geological Society of America, and received the AGU's Whipple Award in 2018 for his outstanding contribution to the planetary sciences, the GSA's G.K. Gilbert Award in 2008, NASA's Public Service Medal in 2005, and NASA's Exceptional Scientific Achievement Medal in 2003. Professor Christensen is the co-chair of the National Academic's Planetary Science and Astrobiology Decadal Survey and has previously served as chair of the Mars panel of the Planetary Science Decadal Survey in 2010-2011, and also as the co-chair of NRC's Committee on Astrobiology and Planetary Science from 2012-2015. His discovery, which is based on TES instrument of the crystalline hematite in Meridiani Planum, was instrumental, which made in selecting the area for the landing site of Mars Exploration Rover opportunity. He has another honor. He has an asteroid named in his honor called asteroid 90388. Phil Christensen discovered by Catalina Sky Survey in 2003. With these words, I invite Professor Christensen to deliver today's Vyakhyaan on infrared eyes exploring the solar system using infrared instruments. Welcome, sir. Over to you.
Thank you very much. That was a very nice introduction. And it's really a great honor to be here today to help you celebrate. I've been looking forward to getting a chance to talk with you, and I would very much like to hear more and learn more about your future plans in planetary exploration. You've done some fabulous things, and I'm looking forward to all the great things that you are going to do going forward. What I thought I'd do today is give an overview of some of the things that we've done and a little bit about the future. I'm assuming that there's a fairly broad audience of background and interest. So I'm going to try to present, again, sort of a high-level view of the types of problems we've been working on and some of the things that we've managed to learn using infrared observations. I'll start by saying that it's been as was mentioned, I've been doing this for a long time. And I've had the wonderful opportunity to work with just a remarkable group of individuals. Obviously, I wouldn't be here talking if it wasn't for all the engineers and students and scientists that I've had the opportunity to collaborate with over the years as we've worked on these different projects. I'm going to talk about two different types of infrared observations today. We use both. I'll talk some about infrared spectroscopy. We've built instruments that actually measure the full infrared, mid-infrared spectrum, usually from about 6 microns out to 25 to 50 microns. And so we use that spectral information to identify specific minerals and use that to better understand the geologic processes. So down at the bottom, you see a couple of the instruments, the infrared spectrometers that we've built. We've also built multispectral infrared cameras that have 3 to 10 filters. And you can see an example if you take 3 filters at say 8, 9, and 10 microns, take an image of those and display them in false color. You see the example there. Now you're taking that spectral information where different minerals have different absorptions at different wavelengths and using that to generate multispectral imagery that you can't do as good a job at identifying the composition, but you can get some idea of that composition. And I'll talk a little bit about that. We've built an instrument like that that's gone to Mars. And then you can also use this information for temperature. That's actually where I got my start in this field, is using thermophysical measurements to get at the physical properties of the surface. So we're interested in the mineralogic composition as well as the physical properties, and the infrared data let us look at both. I like to say, for better or worse, this slide sort of summarizes my life for the last 40 years. These are the various instruments that we've built. For the first half of my career, we were building them with an aerospace company based in California. And for the last decade, the ones along the bottom, we've actually built right here in-house at Arizona State University. So we've developed the capability to build these instruments in a university setting. And I think that's been really remarkable opportunity to engage more students and to really work more closely with the scientific and university communities. Just a little bit of background. So the way the thermophysical measurements work, we try to take observations throughout the day. What you see here is a thermal model of how different materials heat up and cool down during the day. And at the bottom, you see two examples from our Themis instrument at Mars. Um, in short, very fine-grained materials, low inertia materials, low conductivity materials, they can't conduct heat into the surface, so during the day they get very hot. And so you see that blue curve as an example of that fine-grained dust and sand can't conduct heat in, and then conversely, it can't store heat. So at night, it loses that surface heat very quickly. There's no stored interior heat, and so they get very cool at night. Rocky material, on the other hand, has a higher thermal conductivity. It can conduct that heat in during the day. So like in that black curve, it stays relatively cool during the day. And then at night, it has all that stored heat that conducts back out. And at night, then it stays warm. And so by looking at the day-night temperature differences, we can actually get a very good quantitative estimate of what the physical grain size, particle size is of the material. And you can see that really nice example at the bottom where there's materials that are clearly different in their physical properties. The ones I've highlighted there get very hot in the day and cold at night, and so they're finer grain material than their surroundings. I'm going to talk a little bit about what we've learned from this. This was the very first thermal infrared temperature map made of Mars by my PhD advisor, Hugh Kiefer, and one of his students, Jim Zimbelman, back in the 70s. We literally, back then we collected the data and literally hand contoured and hand colored the data. We've come a long ways in our image processing capabilities. But even back then, we saw that the surface of Mars could really be divided into what we called, sort of continental scale temperature units, where some of them stayed very warm at night, shown in these red colors. Other very large areas of Mars got very cold at night, that very low thermal inertia as shown in these blue colors. Since then, we've obviously sent additional instruments to Mars. This is a map from the 1990s from our first spectrometer that we sent. And now you can start to actually see the correlations between the temperature, the physical properties, and the geomorphology and the geology. And what's really interesting, from this, I'd like to, get people thinking. From this image, you can make the argument that it doesn't rain on Mars. And the reason I say that, what we find on Mars is these very large volcanoes, these very high elevation regions, have the finest grained material. So the blues here, the cold material is dust. Whereas the low regions, these channels and outflow channel systems have the highest, largest particle sizes. And that's exactly opposite of what you see on the Earth. In a system where it rains, you wash that fine grain material off of the high elevations, and the finest grain material collects in the low elevations. And we see the exact opposite on Mars. And we think that's because Mars is dominated by wind aeolian processes. So at the low elevations, you have a denser atmosphere. The wind can be more effective at moving material. And so the fine grained materials are swept away at low elevations. Whereas at high elevations, the atmosphere is very thin, the winds are very weak. And so any fine grained material that collects at higher elevations cannot be removed. And so on Mars, we can infer from these data that Mars is currently a planetary surface that's dominated by wind processes that are scouring fine-grained material at low elevation and depositing that fine-grained material at the higher elevations. There's a lot else going on in these images, but that just sort of gives you a sense of the types of processes that we're attempting to study using these temperature measurements. I'm going to zoom in a little bit and just sort of show some examples of how our data have improved. So looking at this red box, again, this is still Mars Global Surveyor data. We're going to zoom in one more time to this little red box. So in 20 years ago, this was sort of the level of temperature data that we had for Mars. And from our Themis camera now, this is that same area viewed with the Themis infrared camera. We can zoom in even further, and now you can actually start to see temperature differences that are related to the physical properties of individual lava flows. And so now we can really start to look at the structure of those flows, the age of those flows, and really start to say a lot more about the geology of the surface. So it's been a real revolution by being able to go to these higher spatial resolutions. Just for fun, we've taken all of that temperature data, converted it to thermal inertia and albedo of each grid point on the surface. And then using a thermal model, you can predict what the temperature would be at any time during the day. We've actually only, we measure the temperature at 3 p.m. and 3 a.m., but from that we can create these models, and you can see how these different physical properties, these regions with different physical properties, heat up and cool down during the day. So it really does provide a remarkable window to look at the nature of the surface. I mean, you can clearly see large regions of Mars that have different physical properties than their surroundings. Okay, so what's going on Mars today? Mars is an interesting place. I've studied it much of my career. Much of the interest from NASA is to look at the ancient Mars. As you know, NASA's working with other international partners is in the process of developing a Mars sample return set of missions that bring samples back. Those are focused really on the ancient rock, what was going on 4 billion years ago that's recorded in those rocks. But what's going on today? So what is the current activity? What are the processes that are going on the surface today? And these temperature measurements really give us a really nice view of that. So again, this is an example, sort of a global view. You can see the scale bar down at the bottom. Again, this is nighttime temperature, and so the red units are the coarse-grained material that holds its heat at night. And you can see there's some correlation with the geology. But as we zoom in, I'm going to look at just an example here. So just looking at one of the floors of one of these outflow channels, these are the Themis high-resolution data. Again, in this case, the temperatures, the colors represent temperature. And now we can see that the floor of this channel is actually exposed bedrock. It turns out Mars is a very dusty place. There's a lot of dust. There's a lot of sand. But because of these really strong winds that we think are channelized down these outflow channels, it's actually much more so than the Earth. There are places that have exposed bedrock. There are very few places on the Earth where you can walk and you're not walking on some type of soil or regolith. But on Mars, this channel is, tens of kilometers wide, and along the bottom, if you were walking there, you would literally be walking on, pretty much intact, solid bedrock. So again, it's quite different than the Earth in that there's not nearly as much regolith and soil development as we see in places on the Earth. This is just another example of how you can use these temperature measurements. This, I'm going to just start. This is the nighttime temperature. So again, the cold regions, the dark regions here are places that get cold at night, and the lighter tone regions are staying warm. There's obviously a lot of pattern and a lot of structure, but if you take those data, colorize them, and then drape them over the daytime imagery, you can now begin to see the remarkable detail and the remarkable correlation of the physical properties with the morphology. And so in that region, the bluish regions, blue-green materials, again, they're getting cold at night, they're relatively fine-grained. Those are active sand dunes. And we can actually, from these thermal models, we can derive a quantitative estimates of what that grain size is. And these are dunes that are probably in the, 200 to 300 micron region, size range. And so again, they're perfectly normal, typical active sands, but they're blowing across, some of those red regions again are bedrock. And so you have this surface that's being, eroded to expose rock, and then those sediments are collecting into these dunes that are active today. And if you look, this is again one of my I really like dunes. I like to study them, but they're just beautiful. And this is an example from the high-rise camera. You can see the scale bar, just the remarkably high resolution imagery of some of these dunes, and you can see clearly from their morphology that they're active. They have beautiful fresh slip faces. But again, this sort of shows that the imagery clearly says it's dunes, and then from the temperature data, we can say these are 200 to 300 micron sized sand particles that again is very much what you'd expect to be the particles that would move by saltation in the current Mars environment. So these data are telling us that Mars is a very active place today. Switching gears just a little bit to look at the other information. What can we learn about the composition of the surface? Again, I'll just touch on this. Obviously, I know many of you, work in this area as well, but these minerals have these beautiful, unique spectral signatures that are related to their crystal structure and their mineralogy. And so each one of these minerals has a diagnostic infrared spectrum, and we can use that information then to collect spectra like these and then derive what the composition of the Martian surface is. This is an example from the TESS instrument. The red curve in that plot is the actual Mars data. There's a gap around 15 microns because of the absorption by CO2 in the atmosphere. And then the black curve is a numerical fit using a least squares fitting approach to take a library of minerals, in this case, a plagioclase feldspar, a pyroxene mineral. We take that library, we do a least squares fit and say what combination of minerals at varying abundances provides the best fit to the measured spectrum. If you do that for hundreds and hundreds of thousands of spectra, you can actually make for each pixel, each spot on the ground, each spectrum, you can derive the composition, and then you can grid that information and make maps of the mineral abundances on Mars. Unfortunately, much of the planet is covered by dust, and that masks the composition of the underlying material. But in the places where the surface doesn't have a lot of dust, we can actually do a very nice job of deriving the mineralogy. And what we found is, for the most part, not surprisingly, Mars is a basaltic planet. But we can say more than that. We can actually talk about the composition of those basalts, look for how the basalt composition has changed, the volcanic composition has changed over time. And what we found is there are probably 4 or 5 different types of volcanic materials. They're all very similar. They're all very close to basalt, but there are subtle differences in that the igneous petrologists can then, chew on and say more about how the interior of Mars has evolved over time, how the composition of the lavas erupted on the surface has evolved over time. And so we could spend a lot of time talking about just the volcanic evolution of Mars using these data. There's another really remarkable discovery we've made. This is a region near the equatorial region of Mars, is part of this massive canyon and outflow system. These canyons that you see here, the scarps are in this region, they're probably 4 or 5 kilometers high, and so it's this very eroded, faulted region on Mars. But if we zoom in and look at some of those areas outlined in black, what we see is, again, the colors represent composition, and we can identify these very olivine-rich layers. They're exposed in the walls of these canyons, and we've been thinking about this for a long time, trying to figure out what these are. And again, if you note the scale, these outcrops of olivine-rich material are occurring over literally 1,000 kilometers of lateral extent, and yet at almost exactly the same elevation, exposed in the walls of many of these canyons, we see this 100-meter thick layer of olivine-rich basalt. And one of the hypotheses that I've been working with several of my students is that this is actually a layer of an ejecta layer. So it could be a massive outpouring of olivine basalt as a eruptive lava unit. Another possibility is it's an ejecta layer from one of the extremely large early impacts on Mars that actually sampled the mantle, the olivine-rich mantle of Mars, and put out this layer of ejecta, which is now, and then 4 billion years of geology, layers and layers of lavas were erupted on top of that, but now we see these eroded outcrops. So again, one possibility is that this literally represents the mantle materials of Mars that have been exposed by a very ancient, very large impact. That's one possibility. As you know, one of the things that makes Mars fairly unique is the presence of water. There's been a lot of, the common joke is, we're always, we're rediscovering water on Mars. But it is of great interest. And the types of minerals, the types of environments where those minerals form tells us a lot about the early conditions on the Martian surface. So as was mentioned at the beginning, one of the things that we did discover was the presence of this mineral hematite. On the left, you see just a global map of Mars to put things in context. The red box then is this area at the equator, and on the right, I'm showing this is an abundance map. So I apologize, and the colors are meaning different things in many of these slides. But here, the colors represent the abundance of hematite. So we use the spectral data to identify hematite. You can actually, from the depth of the spectral bands, you can quantify how much hematite is present, and then you can make a map colorizing that abundance. So in this case, reds represent maybe 10, 15% of the surface covered by hematite, and the blues and greens are at the 5% level. But over much of the surface, we see no hematite at all. It turns out there are three of these deposits. They're relatively small. They're a few hundred, they're a few hundred kilometers in size, but they're remarkably unique. And so, 20 years ago, we made the case that hematite forms most commonly in water environments on the Earth. And so we convinced NASA that this would be a really interesting place to send one of the early rovers to go investigate. Was this indeed ancient lake bed surface? It's extraordinarily flat, and it has the appearance of a deposit, a sedimentary deposit. So we sent this rover to investigate these to see what it looked like. This is the view from that rover. I'm sure you all have seen these before, but first of all, it truly is a remarkably flat surface. Looking off to the horizon, this dark material that you see on the surface is indeed these little spheres of hematite that were being eroded out of the rock. And once we landed, if you look more closely, you see not only hematite, but you also see sulfate minerals. And so this entire stack of geologic units did indeed form in water. The current hypothesis is this was more of a groundwater effect, but the fact that it's so flat suggests that there may have been standing water, or that it certainly was a surface that got eroded down to an extraordinarily flat level. So again, the discovery from orbit of hematite led us to study an environment that truly is very interesting in the amount of the role that water played in the formation of this surface. We've made other observations. This is again a sort of a compositional image. The colors here represent different compositions, and this unusual blue color. We've analyzed the spectra, looked at it, and it's consistent with salt, just good old-fashioned, halite table salt. And so we've been able to map these units, and throughout the southern highlands of Mars, there are literally hundreds, thousands of these small outcrops, exposures of salt on the surface. Mars gets there's a lot of attention played to clay minerals, other minerals on Mars that formed in water. But I believe that we are currently really underestimating the importance of salt, the role of salt, and to have this much, salt minerals exposed on the surface, that those salts probably evaporated from very salty, briny water. So it says, there was probably standing water, groundwater that was very salt rich early in Mars history. And the amount of salt that we see on the surface is really remarkable. And so I think, we really need to understand what is the role of salt, and how important it was in the early history of Mars. Another thing that we've done, this is some work that a colleague of mine, Steve Ruff, has done. The images are from the Spirit rover, looking down on the Husband Hills region. And that rover, I was actually able to drive, tens of kilometers across the surface. And so you see highlighted here two different outcrops, two different hills that we were able to observe on the ground. And if you look at the infrared spectra that we acquired from the mini test region, you can see that there's just a beautiful match of the spectral features to different minerals. Carbonates, we've been interested looking for carbonates on Mars. They tend to form in water. And so this is, again, this beautiful example of actually discovering rock units that had both olivine, which is a primary igneous mineral, and the presence of olivine and carbonates. And so we've actually found outcrops of carbonates that probably, again, formed precipitating out of aqueous aqueous solutions. So just to sort of a highlight, one of the things that I think various types of spectroscopy, including infrared spectroscopy, has shown us is that Mars has this amazing diversity of environments. Carbonates, chlorides, hematite, they all form in different conditions, different pH levels, different temperatures. We find the silica deposits, for example, probably formed in hot springs. And so for me, what makes this so exciting is it's saying that not only did Mars have water, but it had water in a variety of different environments, everything from very saline, salty, briny water to high pH, low pH, acidic water where hematites and some of the sulfates may precipitate, to hot springs where the silica deposits may form. So it's this very rich type, set of environments. And so in the search for life, one can say, okay, we have this wide range of environments where life could have begun. And so it really gives us this diverse set of places to look on Mars to try to understand, where life could have started if it did. I'll just say a couple words about subsurface ice. I think that the next 20 years of exploring Mars is really going to focus on ice. This is some work from one of my students, Josh Banfield, a while ago, I won't go into the details, but using the temperature and how it varies throughout the season, we can actually probe the subsurface and say, is there high conductivity, dense ice beneath the surface? And so using those temperature measurements, Josh made these maps that show the modeled predicted depth to ice. And it says, ice is not exposed at the surface of Mars today, but it is down 10, 20, 30, 50 centimeters beneath the surface. It appears that there are lots of places on Mars where there is ice, just beneath the surface, certainly close enough where organisms or certainly humans someday could access that ice, use that ice as a resource. One of the things that Josh model predicted is when we sent the Phoenix lander to Mars, it landed on one of these regions where we predicted the ice was about 10 centimeters beneath the surface. And sure enough, when we landed, this is the view from underneath the lander. As the descent engines were firing, they removed that surface regolith, and these light tone, dense white materials, that is indeed ice that was exactly 10 centimeters beneath the surface as predicted by these temperature measurements. So just for a teaser, I mean, I think the temperature measurements will also provide a lot of information about the subsurface properties as well. Just a last couple of comments. Another fun thing we've done with temperature measurements, this is the asteroid Bennu. The OSIRIS-REx mission went there. For scale, it's about half a kilometer, about 500 meters across. So it's a relatively small asteroid. But you see on the surface these massive blocks of material. They're the size of apartment buildings. They're these very large blocky material. And so we did the same thing. We measured the temperature, we computed the thermal inertia, and to our great surprise, this is a temperature map at noon, and that arrow highlights that huge rock and boulder. I mean, again, it's just, it's 50 meters across. And if it was a dense rock, you would expect it in the middle of the day to be cold. And instead, this very large rock is the warmest thing on the planet, on the moon. And so these are temperature measurements. The blue dots represent that very warm giant block. And they're very hot, and you can derive the thermal inertia. That thermal inertia is the equivalent of just really porous material. So instead of being dense rock, which is what it looks like from the image, you could take that rock and just crush it in your hand. It's very light, fluffy, porous material. So again, the temperature data has told us something really fundamental about this surface. OSIRIS is in the process of bringing some of this material back. But what it says is, what these temperature measurements say is that it's possible that most of the meteorites that we have in our collections may actually not be representative of what's on the surface of most asteroids, because it's very likely that this very friable, porous material, this low inertia stuff, couldn't survive, coming through the Earth's atmosphere. So it truly is amazing that what look like really blocky materials on these asteroids are in fact, quite porous, probably, quite fragile, and may not actually be represented in our meteorite collections. Okay, just a couple last comments about looking to the future. We are in the process of building an instrument to go to Europa. It's an infrared camera. Its goal is to measure the temperature of the surface. As you know, Europa has these fractures. Its surface currently is covered with water ice. It's very, very cold. But these fractures suggest that there's activity going on, sort of the equivalent of plate tectonics going on the surface, and that we have other evidence that there's a liquid ocean underneath that ice crust. And that ocean is convecting, it's moving the ice crust around. And so one of the things that we hope to do is look at these fractures and see how warm they are as that water is rising along those fractures. If it has erupted recently on the surface, or if it's near the surface, then these fractures will be warm. And so this is just a simulation of what our Europa Themis imager might see. And so the goal is to try to figure out how close the liquid ocean water is to the surface by measuring the temperature of the ice. And if that water is close, then the ice will be warmer. If it's erupted recently on the surface, then we'll still see that thermal signature of that recent ice. So I'll close. This is, we're about to deliver the instrument literally on Sunday. We're driving it to the Jet Propulsion Lab where it'll be put on the spacecraft. It'll launch in a couple of years. And this is just an infrared image we took with that camera to just give you some sense of how well it works, the detail that you can see. This is the ASU campus. So hopefully someday in the not too distant future, we'll have temperature images of the surface of Europa from this camera, and we'll try to probe and determine more about the ocean and its properties. So I hope I've given you a little bit of a indication of some of the things you can do from temperature measurements. I think they make great contributions to our understanding of planetary surfaces and surface processes. As I said, I think ice and icy worlds is going to be extremely interesting in the next decades. And I think, infrared measurements will play a real role in trying to learn more about ice and water throughout the solar system. So I will stop there.
Thank you. Thanks a lot, Professor Christensen, for this very informative and interesting talk. You have covered almost a full solar system, starting from Mars and going to icy planetary bodies. And it's really amazing to see this diversities found in this wide range of Martian environment. It's like we have basically gained a lot of new information from this talk, and I'm pretty sure that we are going to have very interactive question answer session. So now I request all participants from WebEx to please raise your question. You can raise your hand and you can ask questions. So I can already see hand raise. So Dvijesh, can you please unmute yourself and ask question?
Yeah, thank you, Phil, for your excellent talk. So I want to know a few comments from you on Venus. So recently, a phosphine has been detected by radio measurement, but if you see the infrared measurement, the concentration is very less. So do you have any comment on that or any explanation?
I apologize. I missed the first part. Where was the emission coming from?
The phosphine has been determined using radio measurement on Venusian atmosphere.
Yeah, I honestly I don't have any thoughts.
Okay.
I know of that measurement, but I really can't. I don't have anything useful to add, unfortunately.
Okay. Also, my second question is also Venus related. So the Venus surface is very hot actually. Temperature is very high, and also pressure is almost 90 atmospheres. So what kind of analytical setup is required actually for carrying out the infrared spectroscopy in the laboratory? So if we want to prepare a robust mineral database, So it's a very challenging task, but if you have any comment.
Yeah, we once looked at trying to put an infrared spectrometer on the surface of Venus, and unfortunately, it's a CO2 atmosphere, carbon dioxide atmosphere, and the absorption of CO2 at those pressures is so extreme that the atmosphere is essentially opaque at the long wavelength IR. People have succeeded at shorter wavelength IR at seeing through the atmosphere even to the surface, but at these longer wavelengths, I think it could be extremely difficult to see to the surface. One of the things I didn't even touch on today is, I'm sure many of you know, the infrared is extremely useful at looking at gases and clouds and atmospheres. So I think there's a lot of people have done a lot of work with infrared measurements of the Venus atmosphere, but I think it's going to be very challenging to try to use these types of wavelengths to learn more about the surface.
Thank you. Thank you very much.
Thank you, Dvijesh. So we have a couple of hand raised. So I request Professor Varunshi to please unmute yourself and ask your question.
Yeah. Hello, thank you for the interesting talk. My question is related to the dust optical depth. I think Tess and Tennis has done a wonderful job. It has seen, I think, almost a few years of dust optical depth in the atmosphere. So, in fact, it is giving us a very good picture of the dust loading. So, now my question is that is it possible in the future to design such an instrument to look at the diurnal variation of dust loading in the atmosphere?
Absolutely. Again, I'm a geologist by training, but I find the atmosphere extremely interesting. And I think, yeah, atmospheric measurements, looking at dust abundance, looking at water ice cloud abundance is going to be extremely interesting for places like Mars, where there's enough of an atmosphere to actually, be of great interest, and that the atmospheric properties do definitely change through seasons and from year to year.
Okay, thank you.
Thank you. Vijay, can you please go ahead?
Thanks, Dr. Phil. My question is related to the salt deposits on Mars. So do they have any correlation with RSL sites? Because in RSL, we mostly see on crater walls. So do the RSLs on the crater walls are exposing the old salt materials?
That's a great question, and we've been looking. There's not a very good correlation. It's a very weak, so most of the RSLs are in the southern highlands and the cratered regions, and that is where we find most of the salt deposits. But so far, we haven't seen really clear evidence of places where there's RSLs and salt deposits. I personally think that there's a lot of salt in the regolith. I wouldn't be at all surprised if salt is related to the RSL formation. I had a student several years ago who looked very carefully. If these recurrent slope lineae, people have thought that maybe they're water related. If they had been going on for long periods of time, and if they were salty, briny water, then at the base of those deposits, you might expect to see a buildup of salt. We didn't see any evidence of that. So it's a negative result. But from that, we were able to put some limit on, how much water, how much salt. So we didn't see any direct evidence of salt deposits with the RSLs. But again, it could be that just it's very small amounts of salt. which are difficult to detect. You know, it's very tiny amounts of salt are hard to see, and so it's possible that salt is related to the RSL formation.
Yeah, I have one more question. Like, if you look at the thermal inertia map or the dust index map over the Olympus mounts, so the wind is going to be different on top of the Olympus mounts. So it should remove all the dust or the fine-grained regolith material. But why it is, we are not seeing it. Still, we are seeing a fine material. It should be removed by the wind by this time. So why we are not seeing that?
So I think, I mean, my argument would be, you know, those volcanoes are extremely high. You know, the top of them are 25 kilometers high. The scale height of the Mars atmosphere is about 10 kilometers. So when you go up 10 kilometers, the pressure drops by a factor of 1/E. My argument would be that at those very high elevations, it's almost a vacuum. And so the wind up there, there's very little air. And so the winds at those high elevations is very ineffective. You know, there's no wind to sort of move stuff. So what I think is happening is you have these global dust storms that raise dust, and it just sort of, settles out of the atmosphere, and the dust that settles at those very high elevations, it's very hard for the wind to remove because the atmosphere is so thin. And so over time, it collects up there. Now, a really interesting question that I looked at a long time ago is those dust deposits are only a meter or so thick. We can still see rocks through them. And if this process has been going on throughout all of Mars history, you'd expect those dust deposits to be much thicker. So what I think is happening, this is just an idea, is that the winds on Mars change. And so over time, you erode that material and put it somewhere else. How you do that, one of the ideas that we came up with is that maybe dust devils act to raise that dust at high elevations. So there's certainly something going on. There's still a lot more we have to learn about the cycle of dust, where it comes, where it goes, because these dust deposits can't have been accumulating for 4 billion years, or they should be much, much thicker. So I think the dust cycle of Mars, and people spend a lot of time talking about water on Mars, but I think the dust is also is very interesting as well.
Yeah, thanks.
Next question is by Professor Porwal. Professor Porwal, can you please unmute yourself and ask your question?
Yeah. Thank you, Megha, and excellent talk, Phil. I just wanted to find out if you could get some signatures of felsic rocks on the surface of Mars using thermal infrared.
You can, and we've seen some. Most of the rock has 20-30% felsic plagioclase minerals. But one of the things that I really like about the infrared, the near infrared, which is also extremely useful, people use it a lot. It's very good for identifying minerals that have iron in them. So the iron-rich volcanic minerals are great, but the near infrared has a very hard time seeing felsic rocks, things that don't have a lot of iron, whereas the thermal infrared sees them beautifully. We've actually found a few places on Mars where there are very silicic rocks, things you'd call a dacite. And they're small, they're associated with some small little volcanic domes, but you definitely see higher silica and felsic rocks, and the IR works beautifully to find them.
Yeah, thank you. A follow-up question, Phil, here, because we try to work with both short infrared and thermal infrared, particularly from Themis. So one problem that we were always facing was to get the emissivity and come up with these emissivity spectra even at very coarse spectral resolution. And that problem, any thoughts on how we can go about it?
Um, it's you're right. It's a very big problem. I would love to someday combine the two, have the spectral resolution of TESS and the spatial resolution of Themis. That requires a very big instrument to do that. But someday someone's gonna do that. One of the things we've tried to do is use the TESS data where we have good emissivity, we have good spectra, and look at TESS data of Themis data of the same region, and then try to tie the Themis emissivity to the TESS emissivity. That's one way. The other challenge, as I'm sure you've seen, is the atmosphere varies on Mars, and so removing the effect of dust in the atmosphere is a challenge. So unfortunately, a lot of what we've done with the Themis data goes similar to what I was showing today, that you can see spatial variations from the Themis data, but it's difficult. It's been more difficult than I hoped to try to go back and actually say, can I extract an emissivity spectrum? You can do it, but it takes a fair amount of effort. And our success has come when we tied that to the TESS spectra to get sort of to remove the atmosphere and say, okay, this is the emissivity, and then look at the spatial variations within the Themis data. I'm sorry, that wasn't a very satisfying answer.
Well, thanks, Phil. I understand that. I would be really very happy to find some granitic type of composition of Mars, because that would really tell us there's been a lot more fractionation going on Mars than we do expect. And I think thermal-infrared is the only way we can go about it.
There's Josh Banfield, who unfortunately passed away a few years ago. There was a paper that Josh led probably about a decade ago, where we found some very small little outcrops of what looked like granitic rocks. There's a lot of discussion about what they really are, but they definitely have much higher silica content than most of Mars. So we found tiny little evidence, but you're right. And unfortunately, the saddest part of all of this is these giant volcanic regions, which would be fascinating to study, are covered with dust. And we just can't see through that dust. So I wouldn't be at all surprised if underneath that dust is some pretty interesting volcanic units, or you just can't see them.
Yeah, thank you, Phil. Thanks a lot.
Sure.
Yeah. Next question I take from chat box. So Alka is asking why dust is mostly constrained to the equatorial region of Mars.
That's a really good question, and that's where I started decades ago. It's going to be hard to explain in just a minute, but I think it has to do with the circulation pattern, the wind patterns on Mars. Mars goes through these obliquity changes where the tilt of the rotation axis varies, and so at the present time, the strongest winds, the summer is occurring in the southern hemisphere where Mars is close to the sun. So you get very strong winds. They pick up the dust, and on Mars, the Hadley cell can actually cross the equator. And so you erode dust in the southern hemisphere and you transport it, and it deposits mostly in the north. On a 50,000-year cycle, that reverses, and now the strongest winds are in the northern hemisphere summer, And I think you erode the dust from the north and transport it back to the south. So I think there's this north-south transport of dust that's been going on for, much of Mars history. And so I think that explains why the dust deposits aren't hundreds of meters thick, because I think you're moving dust from north to south. And I think it's the fact that most of the dust is in the equatorial region is related to that's sort of where the transport, it's being, deposited, eroded and deposited underneath these, Hadley circulation cells. Now that's just, that's just an idea, but you're absolutely right. Most of the dust is in the equatorial region, and at the present time, most of the dust is in the northern mid latitudes. So maybe there is a cycle that moves it back and forth.
Okay, thank you. This question answer session is really getting interesting now. So next question is Dr. Asu. Amit, can you please unmute yourself and ask your question?
I have one question. You have shown that the area north of Hellas and south of Isidis Basin has plagioclase rich and clinopyroxene rich composition in comparison to the rest of the Martian surface. So I wonder what could be the geologic process that resulted those materials or minerals enriched at that region. Any primary, secondary?
A very good question. As I said a while ago, the sad thing is, much of Mars is covered with dust, and so we have to be careful. We can only see the surface in regions where the dust has been removed, and so some of the spatial pattern we see is influenced by the fact that large regions like to the north and south of that are covered with dust. So my guess would be if we could remove the dust and see the entire surface, what we would see is much of Mars is covered with pyroxene, plagioclase, basaltic type compositions. One of my students, Deanne Rogers, has done some fabulous work. Former students, she's now off on her own doing great work. She's done work where you can actually map probably 5 or 6 different compositional types across Mars. They're all basaltic, but you can see variations in the amount of plagioclase and the amount of pyroxene and the type of pyroxene and the amount of olivine. So there are these compositional differences. We think they're probably due to the evolution of the mantle, temperature changes in the mantle, so that over time you're erupting different compositions of lavas onto the surface. So that's one possibility. The other is that there are just large differences in the composition of the Martian mantle, so that you're getting different regions are erupting slightly different compositions of lavas. So there are differences, and I think they're related to these interior properties, but that's, again, we have a long ways to go to really prove that.
Thank you.
Hello. Yeah, thank you. So is there any other question from participants?
I have one more question.
I have a question. I'm like a bit ignorant about this modeling what you do. So basically what I understand is from this infrared instruments, you are getting this temperature variation. So basically the temperature map of any planetary body. And then what kind of this initial conditions you have to use in your model to get this physical thermophysical properties. Basically, for example, if we consider Mars or Moon, at least we have some idea. But when you are looking to Bennu or Europa, what kind of challenges would be there?
So a great question. So these thermal models, people have been developing these thermal models for a really long time, and they've gotten very sophisticated. They basically start sort of from a first principles. So for example, on Mars, we have to assume that there's a gas in the pores. So you model the thermal conductivity within the grain, between the grains, where the grains touch, and then the thermal conductivity of the gas. And so if you know the conductivity, so sorry, you go into a lab, you take a lot of different particle sizes, and you measure the conductivity as a function of particle size for different materials with and without gas in the pores. So from that, you can say then I can take the temperature measurements on Bennu, that it's in a vacuum, and relate those temperature measurements to laboratory measurements we've made of different particle sizes, and say, for this temperature behavior throughout the day, I can equate that to a particle size that I've measured in a laboratory. So once you know if it's a vacuum or has an atmosphere, you can relate that to laboratory measurements that then let you go from the temperature to the particle size.
Thanks. Dr. Durga Prasad want to ask you a question. Durga, please go ahead.
Thank you, Professor Phil, for an excellent talk. You have deciphered the the potential of thermal infrared measurements and its application to all planetary bodies. It's really very interesting. I had actually one question which Megha has already asked, the same thing, but I have a follow-up question. In one of your slides, you have shown that using thermal infrared measurements, we can actually tell about the ice distribution and depth of ice, of course, using the seasonal variations also. So indeed, it requires a very complex thermophysical model. So what do you think are the primary constraints for that? Means what are the constraints which we should definitely consider and what we can ignore?
I think the biggest constraint, the biggest limitation, is how deep you can sense. In other words, if the ice is probably more than a meter down, meter and a half down, it's not going to have a signature, a thermal signature at the surface. And so I think, unfortunately, I think we can do a good job of detecting ice in the upper meter, but below that, it's difficult to do with temperature measurements. The other thing is, what works really well is to have day and night measurements over a long season, and that allows you to separate the effect of the diurnal effects due to the uppermost, the properties of the uppermost 5 or 10 centimeters, separate those effects from the deeper thermal effect due to the ice. So you need really good time of day measurements over long seasons. But I think if you can do that, then you can separate out the different, the effect of the atmosphere, the effect of the physical properties of the upper 5 centimeters, and then the effect of the ice that's down deep. those are, I think, the biggest challenges. But I think there's a tremendous potential for doing that.
So I have another follow-up question. So the thermophysical properties at a micro scale and at a macro scale are significantly different when we look at. So how do we have a conjuncture between which to take under what conditions?
That's another really good question. Some of the recent models, in particular for airless bodies like Bennu and other asteroids like the moon, and again, for us, macro scale is sort of boulder size things. It turns out that if you have a rough surface where rocks are radiating back and forth between each other, that's a very different thermal environment than, say, a flat line surface. So it's particularly important on airless bodies, the thermal models really need to take into account that roughness. So that you're actually accounting for that. For places like Mars, where you have a lot of gas conduction, that's less important. But it's certainly a consideration. For places like Mars, I think that the thermal data, the thermal models we've actually been able to land on some of these surfaces and say, yeah, it really is the particle size that we predicted. So I think the thermal models are working pretty well, but you're right. There are a lot of complexities that you have to take into account.
Okay, I have one final question. So these thermal models, I know that they are indeed very important and of course complex, but for Mars, as there are a lot of observations, a lot of work that has been going on, while there is no any three-dimensional thermophysical model. So if I see the KRC, it's almost, even now it is one-dimensional and it's still evolving. So what do you think is the reason?
That's another great question. I think up until now, I think the simple answer is up until now, KRC has been good enough that there's sort of this, the data get better, and so the models have to get better, and then the data get even better, and then the models have to catch up. And so up until now, a one-dimensional thermal model has been good enough. I think as we get better thermal data and we try to, extend this, we need to go to 2- and 3-dimensional thermal models. The other thing, the KRC and most thermal models do not do a good job of accounting for the effect of the winds and any heat that's advected away from winds. So I do think there's a lot of room for improving these models. And again, all I can say is up until now, they've been good enough.
So you mean now it's the time for looking for 2-dimensional and 3-dimensional thermal models?
Yes, I agree. In particular, as we start to get, more complicated, like looking at ice, for example, that ice can migrate. It can, and so I think we do need more sophisticated thermal models.
Thank you very much.
Sure.
I can see Amit has raised his hand. Amit,
I have one
can
more
you please
question.
go ahead?
Yeah, you mentioned that subsurface ice. So subsurface means these are covered, the ice is covered by soil or rock, basement rock, or both? Means there are sedimentary rocks and that can contain also groundwater, right? So
Right.
yeah. So what type of subsurface material you are talking about, or both?
So I think, again, for us, subsurface means in the upper meter or two. Any deeper than that, you can't detect it with infrared. So what I find really interesting, you know, at the surface of Mars today, ice is unstable except at the very poles. It's just it gets warm enough that, you know, at the mid latitudes that ice is not stable right at the surface. But just because of if you bury that ice under 10 or 20 centimeters of regolith material, then it takes a long time for that water to diffuse out through that soil. And so you can have ice that's 10 or 20 centimeters beneath the surface that can basically be stable for tens of thousands of years. And so that's the stuff that I think is interesting. How did it get there? You know, why is it there? Where did it come from? But we're seeing evidence that to much of the mid-latitude of Mars, there probably is that ice, you know, in the upper tens of centimeters within the surface. And so, you know, what's the story? How did it, you know, where did it come from? And then how did it get buried? Why is it there? I think these are all really interesting questions, but it seems that it's down there.
Thank you. Thank you, Professor Christensen. So is there any further question from participants? If no, then I thanks once again to Professor Christensen for taking all our questions and queries so patiently. And now I hand over to my colleague, Dr. Vinit Goswami, for giving vote of thanks.
Thank you very much, Dr. Megha Bhatt. That brings us to the conclusion of the 42nd episode of PRL Amrut Vyakhyaan. So I would like to first thank Professor Philip R. Christensen for accepting our invitation and giving an excellent talk on solar system exploration and understanding the compositional properties of planetary surfaces using infrared observations in today's episode of PRL Amrut Vyakhyaan. We are also thankful to Professor Christensen for answering the audience's questions. Next, I would like to take this opportunity to thank our audiences on both the YouTube and WebEx platforms. Next, I express my sincere thanks to PRL Director, Professor Anil Bhardwaj, Dean PRL, Professor D. Palamraju, and Chair of PRL Amrut Vyakhyaan Committee, Professor Nandita Srivastava, for all their support in organizing this episode of PRL Amrut Vyakhyaan successfully. I also thank my colleagues in Vyakhyaan Organizing Committee for successfully conducting the 42nd episode of PRL Amrut Vyakhyaan. I would also like to thank Dr. Megha Bhatt for conducting the question and answer session. I sincerely thank you all for being part of Azadi Ka Amrit Mahotsav and PRL at 75 celebrations. Kindly visit our website and other media platforms to know more about the upcoming events being held at PRL, in particular PRL Amrut Vyakhyaan. With these words, I propose the closure of today's episode of PRL Amrut Vyakhyaan. Thank you very much.
Thank you.
Thank you.